we start, I just want to define what an exponential equation is. This is any equation in which we find a variable inside the power. Now, this could mean something as simple as 2 to the power of x is equal to 64, or something way more complicated like the following equation. If x happens to be inside a power of one of our bases, we call it an exponential equation. The goal of this lesson is to devise some strategies to solve these kinds of equations when our base is numerical. Let's discuss the procedure that we can use to solve exponential equations. The first thing we want to do is try to isolate the exponential expression on one side of our equal sign. Now the reason we're going to do this is because of step 2, where we apply the logarithm with the same base to both sides of the equation. The reason we're applying the logarithm to both sides of the equation is because we know if we apply the logarithm of the same base that our exponential expression is in, those actions are going to undo each other because they're inverse processes, and we're going to be left with just the power. Sometimes it may not be possible to use a logarithm with the same base as our exponential expression, or in some cases we have two exponential expressions and we have to choose one or the other base for our logarithm. In this case, don't forget that you have the special power property of logarithms that you can use. So you're able to take that exponent and bring it down out front and treat it as a multiplication. So sometimes you may have to use step 3 to bring down the power to remove it from that exponential expression. And of course, our fourth and final step here is to solve for x, or whatever variable we have in our exponential equation. Let's begin by solving the following two examples. First, we're going to focus on 10 to the x equals 100. Now hopefully you can see that if I were to write this a little bit differently, writing 100 as 10 squared, you can see that the value of x here is probably going to be 2, or at least hopefully this convinces you that the value of x is 2. But let's work through the procedure so you can see exactly what's happening for cases where it's not easy to rewrite this right-hand side as a power of the base that's on the left-hand side. The idea is, because 10 is our base, we're going to take the logarithm base 10 of both sides. Since the base of our logarithm and the base of our exponential expression on the left-hand side are the same, their actions are going to undo each other and we're going to be left with the value of x. The same thing happens over on the right-hand side. The base of our logarithm as well as the base of our exponential expression are the same, so we're left with just the numerical value of 2. So this is the strategy that we use when the exponential equation doesn't simplify quite as nicely as the one we just did. For example, if we have e to the 2x equals 17, well, it's really difficult for us to think about 17 as having base e raised to some power. So what we do is we are going to take this exponential equation and we're going to use log base e to remove the base of e in our exponential expression. So we'll take ln of both sides. Notice here that since this is log base e, and the base of our exponential expression is also e, those actions are going to undo each other and we're going to be left with 2x over on the left-hand side. Over on the right-hand side, we're just going to leave this as ln of 17. That's the best we can do. There's no way that we can rewrite 17 using a base of e. Now finally, to solve for x, we could divide both sides by 2, so we get the following expression, ln of 17 over 2. Next, let's take a look at an example where the bases of our exponential functions may not necessarily be the same. I'm going to use the procedure and I'm going to apply a logarithm of both sides. In this case, you want to choose one of the bases to be the base of your logarithm as well. So I'm going to take log base 2 of both sides just to make the computations on one side a bit easier to handle. Since the base of my logarithm and the base of my exponential expression on the left-hand side are the same, I'm going to be left with 3n minus 5. The same thing does not happen on the right-hand side because the base of my log is 2 and the base of my exponential expression is 4. Now, that said, I can still use the power property of the logarithm here. I can take the n plus 1, which is the power, and bring it down out front and treat it like a multiplication. So on the right-hand side, we're going to get something that looks like this. It doesn't always happen so nicely that this logarithmic expression is going to simplify, but in our case, we can write 4 as 2 squared. And now we can see on the right-hand side that this is going to change into n plus 1 times 2. So I'm going to go ahead over on the right-hand side and expand that through to get 2n plus 2. And now we have a linear equation in n that we can solve very easily. If we subtract 2n from both sides, we're going to get n minus 5 is equal to 2. And we could add 5 to both sides to get n is equal to 7. In our last example, we want to solve the following equation. Negative 3 times e to the x plus 2 plus 12 equals 42. Our first step is to try to get this exponential expression all by itself. So right now we have this minus 3 and this plus 12 that are in the way, and I need to remove those before I can apply the natural logarithm to get rid of the base of e. So let's begin by subtracting 12 from both sides. This is going to leave us with negative 3 e to the x plus 2 is equal to 30. Next, let's remove this negative 3. So I'm going to divide both sides by negative 3. This is going to give us e to the x plus 2 is equal to negative 10. Now that we have the exponential expression all by itself on the left-hand side, now's a good time to apply the natural logarithm to both sides to get rid of this base of e. So the left-hand side does become x plus 2. But did you notice something here that went wrong? Maybe you recall when we started working with the natural logarithm that we can't have negative values inside of our natural logarithm. This implies that there are going to be no values of x that solve our original equation. A logarithmic equation is any equation where we have a logarithm of a variable. So it could be something as simple as log base 10 of x is equal to 5, or it could contain more complicated logarithmic expressions like the following. In either way, what we're looking for is we're looking for our logarithm to have an inside portion that contains the variable. Similar to what we had in the last lesson, we want to develop a procedure to solve logarithmic equations. Now the first thing that we want to do is if we do happen to have multiple logarithmic terms that all contain the same base, we want to combine them using the laws of logarithms. Once we have only one logarithmic expression, we can isolate that on one side of our equal sign. Remember that the action of taking an exponent to a particular base followed by taking the logarithm of that same base, those actions undo each other. So the idea here is to write each side of our equation as a power of the same base as the logarithm. Number 3 might sound a little confusing, so I'll show you through some examples here coming up. Then we're going to solve for whatever variable happens to be in our equation. Now, make sure that you absolutely check your answers. So certain values of x, we may not be able to use them in our original logarithmic equation because logarithms can't be negative. We ran into that problem in the very last example of the last lesson. So let's get to it. Let's begin by solving the following two equations. I'm going to start on the left with log base 10 of x minus 3 equals to 5. Our first goal, if we have only one logarithmic expression, is to isolate that on one side of our equal sign. So our first step here is to remove the negative 3 from the left side by adding 3 to both sides. So if we add 3, we should get log base 10 of x is equal to 8. Now that the logarithm is by itself on the left-hand side, we look to the base of our logarithm. In this case, it is base 10. So because it's base 10, what we can do is we can raise both sides of our equation and use 10 as a base. So here we'll get 10 to the log base 10 of x equals 10 to the 8. And what we've done over on the left-hand side is now we have an exponential expression that's base 10. We have a base 10 inside of our logarithm, so those two actions undo each other, and we're left with the inside portion of our logarithm, which is x. So our final answer over on the left-hand side is x equals 10 to the 8. Next, let's take a look at 7 times the natural logarithm of negative 2x equals to 14. What we want to do in this case to isolate the natural logarithm by itself is to divide both sides by 7. When we divide both sides by 7, we get the natural logarithm of negative 2x is equal to 2. Now, since the natural logarithm has base e, that implies if we take e to the ln of negative 2x, this should be equal to e squared. So these two actions over on the left-hand side are going to undo each other, and we're going to be left with just the inside of our natural logarithm, which is negative 2x. And our right-hand side stays as e squared. Now finally, to solve for x, we could divide both sides by negative 2. So our final answer here is negative e squared divided by 2. In our second equation, we're going to have to use laws of logarithms in order to solve this equation. So here we have log base 10 of x plus 2 plus log base 10 of x minus 1 is equal to the number 1. Now, since both of these logarithms have the same base, what we can do is we can use the laws or the properties that we saw in lesson 5. So here, addition on the outside is going to become multiplication on the inside. So we can rewrite this as log base 10 of x plus 2 times x minus 1. Expanding through the brackets on the inside of our logarithm, we get x squared minus x plus 2x minus 2. And simplifying this one step, we're going to get log base 10 of x squared plus x minus 2. So in order to remove our logarithm, we're going to get the following. We're going to have 10 to the log base 10 of x squared plus x minus 2 is equal to 10 to the power of 1. Since the base of our exponential expression and the base of our logarithm are the same on the left-hand side, we are going to be left with x squared plus x minus 2 is equal to 10. Subtracting 10 from both sides, we're going to get x squared plus x minus 12 is equal to 0. And from here we can factor this quadratic expression. So we look for two values that multiply to negative 12 and add to 1. Those are going to be 4 and 3. And we need positive 4 and negative 3. This leads us to two possible solutions. Either x plus 4 is equal to 0, which gives us x is negative 4, or x minus 3 is equal to 0, which gives us x is equal to 3. However, when we substitute these values back into our original equation, 3 is okay. We get log 5 and log 2, which are both acceptable. But when we try to put negative 4 back in, we get log of negative 2 and log of negative 5, which are not acceptable. So we're going to have to get rid of negative 4 as a possible solution because it creates logarithms that are negative. So in this case, we're forced to conclude that x equals 3 is the only possible solution to our original equation. In our last example, we're going to solve the equation natural logarithm of the natural logarithm of x is equal to e. Now let's work from the outside in. I want to get rid of this natural logarithm, so I'm going to take both sides and I'm going to write them as the power of the base e. Like so. The action of doing that is going to remove this outermost natural logarithm. And we're going to be left with, on the left-hand side, the natural logarithm of x. Alright, we have one more natural logarithm to remove, so this suggests that we should take the base e one more time, like so. And the action of doing that is going to remove both the base e and our natural logarithm, and we're going to be left with just x over on the left-hand side. So a bit of an odd example here, we get x is e to the power of e to the power of e. Alright, my little epsilons, stay positive.